Hi, my name is Hyuk-Jun Yang. Today, I'll introduce you about active learning, focusing on a paper titled Low-Budget Active Learning via Wasserstein Distance, an Integer Programming Approach. Let's get started. Here's an overview of what I'll cover today. So what is active learning? Active learning is a novel learning framework where the system itself selects which samples should be labeled and used for supervised learning. This is because labeling every sample in the data pool is impractical. The framework aims to choose the most informative samples so that supervised learning can achieve good performance even with a limited number of labeled samples. The key question today is which samples are actually informative. Formally, in a supervised learning framework, we aim to minimize expected risk, which is the expectation of the loss function. The algorithm used might be empirical risk minimization, ERM. In this supervised learning context, active learning frameworks should come before supervised learning. The framework selects which samples will be labeled from an unlabeled data pool D, and the name of this core set is C. The size of C is determined by a budget B. Once the core set is chosen, it is labeled by an oracle omega, and the variable pi indicates the indices of the selected samples. The theoretical background here suggests that the risk is bounded by empirical risk, generalization bound, and core set loss. The first and second term do not depend on how we choose the core set, because empirical risk would be minimized by supervised learning, and the generalization bound is influenced by the oracle function. Therefore, by minimizing core set loss by choosing informative samples, we can minimize true risk. Then the authors of this paper provided a new theorem stating that if the loss function is K-Lifshitz continuous, then the core set loss can be bounded by Wasserstein distance between the distribution of the core set and the unlabeled data pool D. Therefore, the key point is that minimizing the Wasserstein distance will minimize expected risk. But how do we actually select such samples in practice? But before the algorithm, let's briefly discuss the definition of the Wasserstein distance. It measures the differences between two distributions. The Wasserstein distance is the minimum cost of transporting components from one distribution to another. In terms of sample transportation, if there's a distance between every sample in the featured dimension, then we need to decide which samples to move to which destinations. If we represent the distance between samples with a matrix D and the selection and transportation method with a matrix gamma, the Frobenius inner product will calculate total cost of transportation, and minimization of the cost will give us the Wasserstein distance. This gamma matrix is also known as the transportation polytope. The under-maximization is a dual problem to the minimization. But we also have to get the minimum Wasserstein distance, although the distance measurement itself is a minimization of transportation cost. So this is a double minimization problem. Therefore, the authors suggested decomposing the problem and using an iterative method called generalized Benders decomposition, GBD. If we reformulate the problem, our aim is to obtain the gamma matrix and pi. This problem is equivalent to the Wasserstein master problem W and P described below. If we find the minimum eta under the given constraint, we get the minimum distance and the optimal pi. Then considering the dual variable lambda, the WMP problem can be seen as a Lagrangian in terms of pi, which can also be interpreted as the Wasserstein distance. However, obtaining lambda is complex, so the authors introduced a relaxed problem named WRMP. Solving WRMP is key of GBD. If we have an approximation of eta and pi, we can determine gamma and lambda. By adding this lambda as a new constraint, new solutions for eta and pi emerge. This is a cycle of iteration. Assume that there's an optimal point eta star and pi star. Since WRMP is a relaxation, eta star is lower bounded by the approximation eta hat. Also, because pi star is the minimum point of distance, eta star is upper bounded by the Lagrangian of pi hat. In conclusion, by continuously adding constraint to lambda in the relaxation, we can converge to pi star and eta star. Therefore, the GBD algorithm works as follows. Start with an arbitrary pi 0 hat from the candidate set P and an empty set big lambda. With a solution eta hat and pi hat at each iteration, we get gamma hat and lambda hat. Adding lambda hat to the constraint set big lambda provides new eta hat and pi hat values. This iteration continues until the Wasserstein distance converges. However, the authors mentioned that this iteration process would be slow. They discovered that since the iteration includes a relaxation problem, it can be accelerated using certain techniques, so this must be applied carefully. One technique is enhanced optimality cuts. This method utilizes primal dual optimization inequalities to push the eta values, tightening the bound and speeding up convergence. These inequalities are shown here. Another technique is pruning constraints. Since the measurement is distance, if we find a good candidate for pi, its neighbors are also likely good and vice versa. In this context, pruning will select pi through a constraint optimization problem where pi must belong to good candidates and avoid bad ones. This is done by hemming sphere around pi hat, and the new pi will be chosen outside the bad candidate sphere and inside the good candidate sphere. To conclude, the GBD algorithm with acceleration is the key contribution of this paper. Assume that we got a distribution D through self-supervised learning. Then with input of budget B and the distribution D, the GBD algorithm will give the optimal core set which minimizes the Wasserstein distance. So this is the conclusion of the GBD algorithm. For justification, authors conducted experiments on two different active learning tasks. The first task is aforementioned image classification with limited budget to assist supervised learning. The second task focused on domain adaptation, which entails a source domain and a target domain. The objective of this is to leverage the distribution of the source domain to select samples from the target domain. For the details of the experiments, the first one used 3 different datasets and used a self-supervised learning method named SimCLR. On the other hand, for the second experiment, they used a dataset named Office 31, which contains 3 different domains. Instead of self-supervised learning, in this time, unsupervised learning method named FDAL was applied. The first experiment is a simple comparison of the objective function of the proposed method, Wasserstein plus EOC, versus K-medoid across diverse budgets. K-medoid is another selection algorithm, and the objective function here corresponds to loss function, so small is better. The result shows that their proposed method outperformed if B was over 120, where in this situation, the selection problem is larger and harder. This experiment focused on early termination with the same setting as before. The results shows that even a short execution time of 3 minutes can achieve competitive performance. In this experiment, the authors compared their method to other core set selection baselines. The x-axis represents the budget size, and the y-axis represents the accuracy of the supervised learning after execution. This result shows that the proposed method is competitive, but there is no single dominant method across different budget size and dataset. This is another experiment, domain adaptation, and from the figure, we can conclude the proposed method is competitive or outperformed. Especially even if the budget is relatively small, the proposed method could tolerate those scenarios, while some other methods showed significant failures. One point is that representation-based active learning frameworks were better than uncertainty-based. In conclusion, the main contribution of this paper is that it proves the theoretical relationship between true risk and Wasserstein distance. Furthermore, the paper proposed an algorithm that can select a core set from the data pool in an integer manner. In addition, the paper presents an acceleration method that can make the algorithm converge faster. This is the end of the presentation. These are references. Thank you for listening.
Hi, I'm Bomgun Park, and I'm going to present the second paper titled Active Running Helps Pre-trained Models Run the Intended Task. First, I'll briefly introduce active running and then discuss the limitations and the problem that active running tries to address. In machine learning, trained models can fail due to task ambiguity. Generally, active running allows models to resolve the task ambiguity by identifying examples whose label would be informative. This figure illustrates an active running scenario in a pool-based setting, which is a common situation in active running. The machine learning models need more informative data to remove the ambiguity. Active running algorithms select informative samples from the unlabeled data. The selected samples are given to an oracle or human annotator to get labeled. Using this labeled dataset and the original dataset, the model is retrained and the task ambiguity can be mitigated. However, active running has often seen limited success in practice. In traditional settings with smaller non-trained models, several problems limit the effectiveness of active running, including label noise, examples that are challenging for models to run, and a lack of generalizability of active learning heuristics. In this paper, the proposed algorithm overcomes these challenges by using a pre-trained model. To evaluate the effectiveness of the proposed algorithm, classification is used as a main task. In classification, the model predicts the rate of the input data based on the probability. Once the model is trained on specific training samples, the probability for the true label is significantly higher than that for the false label. Before diving into the main explanation, I will briefly explain the pool-based setting, which is the focus of this paper. In this paper, we have a pre-trained model M, a small seed set of training data S, and a larger pool of unlabeled data P. With these preliminaries, let's dive into the proposed method. The proposed method procedure proceeds as follows. First, train the model M on the dataset S until it converges. Second, select the points from the unlabeled data P that are deemed most informative according to an acquisition function. This function scores how informative the data is. I will explain the detail of this acquisition function in the following slide. Once the points are selected, obtain their corresponding labels from Oracle until some budget K of data points is exhausted. Then, add these newly labeled points to the original existing dataset S. Using this updated dataset, the original model is retrained for the next acquisition step. This overall process is repeated for a fixed number of acquisition steps. In the aforementioned procedure, acquisition function of the form shown below is employed. This is one of the uncertainty sampling method where we acquire points for which our model is least confident in its predicted label. Let's consider a simple example. In this figure, the given task still exhibits ambiguity. The model struggles to identify whether the deciding feature for the label is color or shape. However, by employing the acquisition function with the pre-trained model, we can select the most informative example based on the criterion of least confidence. The model can be retrained with these selected samples and the task ambiguity can be mitigated as shown in the right figure. In order to evaluate the effectiveness of the proposed algorithm, the author considered a variety of datasets where task ambiguity manifests through a scarcity of particular kinds of examples. Therefore, two kinds of examples are considered in this paper. The first type is defined by combination of causal and spurious features. The second type is defined by unseen attributes that shift during deployment. These datasets provide an empirical testbed for evaluating the ability of pre-trained model to select disambiguating examples using active learning. The following result shows the observation given as follows. For more detail, let's move to the next slide. First, we can easily see that uncertainty sampling outperforms random sampling across all datasets. This figure shows the accuracy of active learning versus random sampling on the validation dataset as a function of the number of samples acquired during training. The second observation is that all types of uncertainty sampling outperform random sampling in iWildCam dataset. Here, two additional active learning methods in addition to least confidence sampling are considered. We find that all types of uncertainty sampling methods are effective on most datasets except ID class 0 and OOD class 0. This is because the ambiguity in this dataset is less than in the others, so there is no need to employ the uncertainty sampling. The next observation is that the uncertainty sampling identifies and upsamples disambiguating examples. The model selects examples with atypical background combination, as one might intuitively hope. For example, in the water bird example, the model identifies and upsamples on the example where previous feature and causal feature disagree. Also, uncertainty sampling can upsample both visible and latent minority subgroups. Not only does the model upsample lower star ratings, which are less common, it is also able to upsample rarer product categories, which is a latent attribute. The fifth observation is that the uncertainty sampling only provides gains when using pre-trained model. In this figure, 5 model is used to evaluate the performance. This model is pre-trained except last 2 models. For this reason, the pre-trained model outperforms random sampling in the most of datasets. The last observation is that the task ambiguity is the key factor driving the success of active learning with pre-trained model. We can easily observe that as these ambiguating examples become more scarce, uncertainty sampling experiences far less of an accuracy drop compared with random sampling. From these experimental results, we can conclude that the pre-trained models can preemptively resolve task ambiguity through active learning, and the active learning helps across a variety of settings where the data is previously corrected, undergoes domain shift, or contains unlabeled subgroups. This is the end of the paper review presentation.